Good evening, everyone. So, today we are on our 15th lecture, and here we will study about the solution to the KdV equation, KdV-Burgers equation, and the Burgers equation. So, in part A, we will deal with the KdV equation. Now, we know that it is the KdV equation is the general form. So, this is n is a nonlinear term, d is a dispersive term, and when these two forces balance each other, we get a standard KdV solitary profile, either compressive or a rarefied. So in order to solve this equation, we put a transformation with the stretched space coordinate and stretched time coordinate tau into a new coordinate, phase coordinate eta. And here m is the Mach number, and we have combined these two. So you want to study the evolution of the KdV solitary structure. Okay, now we have to put boundary condition as xi tends to infinity. We get phi and del 2 phi del xi 2 tending to 0, and as well as del phi del xi, the first order derivative, also tending to 0. So the solution of the KdV equation is phi is equal to phi m sec hyperbolic square eta by delta. Now here we have got two more new terms, phi m and delta. Phi m is known as the amplitude of the solitary structure and delta is the width. So the amplitude is given by 3m by n, where n is a nonlinear term, and delta is equal to root over 4d by m, where d is a dispersive term. So we can see that more the dispersive effects, the more will be the width, and higher the nonlinearity, lower will be the amplitude. Now you see, we have to introduce to you what are the rarefactive and compressive solitons. Now you see, you will, in the literature, you will find compressive, you will find compressive solitary profile, or bright solitons, or someone who see positive solitons, as well as rarefactive, dark solitons, or negative solitary structures. Now when the peak is in the positive direction, starting from 0 here, if it is in the positive direction, we call it a compressive soliton. That means there is a more increase in the density of particles out here. Now for a dark soliton or a rarefactive soliton, solitary structure, it is here in the deep that we find the potential is negative, that is the number of particles out here is less. So these are the often used terms, and what do they look like in reality. So either you can write compressive solitary structure, bright or positive, as well as these things. Now part B is the KdV-Burgers equation. So here the KdV-Burgers equation is something like this. Till this much was the KdV equation. We have included that viscosity term in the governing equations, so we gave it a viscosity factor. Often you will find in the literature viscid shocks or KdV-Burgers equation in viscid media. So there you will find this expression. Now R is a function of eta and all those things, parameters. So is the viscosity term. Now to get the solution, we make the same kind of transformation and we combine these two things, and in order to prove the solution, we get the same boundary conditions, but the solution is somehow different. You see, it is KdV-Burgers equation. So was has given one solution. So they have put it some 10, basically 1 minus tan hyperbolic square is equal to sec hyperbolic square, and this is the shock part. So a profile with a solitary structure and a shock component will be represented by a solution like this. So here you see we have got a solitary profile coupled with a shock, because when it starts from a positive value in the potential, it after on the other side it comes to a negative value. So there is a shock front, which is crucial in astrophysical as well as laboratory produced plasmas. In astrophysical plasmas, in our previous lecture, probably in the 11th lecture, you will find where do we observe the shocks. So you should keep in mind that this is a shock profile coupled with a solitary profile. So that's why these two terms comes. Now the third one is the Burgers equation. As we know that there won't be any dispersive term, only the nonlinear term and the viscous term. So this is the Burgers equation, and you can use the same kind of stretching a transformation and get this as the solution. It's a tan hyperbolic solution. And here you see from here, if we take the shock part, you can see that here it starts with a KdV-Burgers type of form, but at this point it is just a shock front, because here there is no deep or anything. Just from this level, after it crosses the other part, it comes to the positive end. So that's how we get a solution for a Burgers equation. Thank you. Thank you for your attention. So meet you in the next lecture to how to plot graphs. Thank you.